this curve, now we know the value of endurance limit, and remember this value is the ideal value until now, and that is a factor of ultimate strength. So the value of strength of failure at 1000 cycles will also be a factor or a percentage of ultimate strength. So this curve links the value from ultimate strength with the value of strength of failure at 1000 cycles. This will give you the missing point. So we know that endurance limit is 0.5 ultimate strength. Strength of failure at 1000 cycles will be F. This factor F comes from the curve here. So if your ultimate strength is, let's say, 630, ultimate strength is 630, 630 is here. Using this curve, you can read F. F in this case is just below 0.86. So we'll make it, this is 0.85, make it 0.858 for you. Okay? And this will give you a value for strength of failure at 1000 cycle. And now you can draw this curve. You can draw this curve. You have ultimate strength, you have endurance strength, you have strength of failure at 1000. So ultimate strength, which is strength at 0 cycles, this strength is at 0 cycles here, and this strength endurance limit at 1000 cycles, and this strength SF at 1000 cycles. Okay, now we can create an equation for strength life curve. Okay, the two known points are given here at 1000 cycles and at 1,000,000 cycles, these two. Okay, you can use this equation and you can estimate strength of failure at any number of cycles using factor A and exponent B as given in equation 614 and 615 here. So you can use ultimate strength, endurance limit, and strength of failure at 1000 to calculate strength at any points. For example, if I ask you to find strength of failure at 10,000. Okay, so N here is 10,000. You calculate A, you calculate B, and then find strength of failure. This strength of failure will definitely be above endurance limit and below strength of failure at 1000. So it will be somewhere here. In this example, strength of failure at 1000 is 700. Endurance limit is 350. So this strength must be calculated here. Okay, with the same thing, you can calculate number of cycles if you know the applied stress. So it is a reverse. You have stress, and from that stress, you have stress here, you have a reading, let's say stress of 500. This stress can give you number of cycles that you can calculate using equation 616. Okay, so this, everything that we learned here, or this method, the strength life method, is in diagram, can only be used when we have completely reversed stresses. Completely reversed stresses means that we have a machine part or an element or a beam or whatever that is subject to stress that is positive and negative certain value. Okay, for other stress situations, we cannot use this method. Completely reverse stresses means an element is subject to positive and negative stress values. So positive stress is equal to negative stress, just like the case of pure bending test that we saw, or tension compression situation and situations like this. Okay, so this example you can apply for to calculate the number of cycles for different stresses and how to calculate endurance limit. Okay, so the endurance limit that we calculate here is ideal one. The 0.5 ultimate strength is the ideal for a perfect test specimen. Ideally prepared, polished, material is known, no stress concentrations, and so on. If we have different conditions than the ideal test specimen, then we need to adjust the endurance limit. So we start with 0.5 ultimate strength, which is this one. S E prime is 0.5 ultimate strength, and then we add all the modifications factors. We need to modify for the surface conditions. If we have different surface conditions, then we need to include Ka. If we have different size, different diameter, different length, then we need to apply Kb, size factor. If we have different type of load, if load is not bending, then we need to apply Kc. If temperature is different than the ideal test temperature, then we need to apply Kd. Reliability and any other effects that are known, we can also add them to get the corrected and new endurance limit. Okay, so the first factor is surface factor. You can find surface factor just from the material. Usually when we give you steel, we will say this is hot rolled, this is cold drawn, this is ground, this is forged. So from that information you can calculate surface factor from this table 6.2. So cold drawn material is given here, hot rolled material is given here. This gives you factor A, reading for factor A, and exponent B. Can use these to calculate surface factor. The second one is the size factor. Size factor is applied when data is given. Size factor for axial load is 1. There's no size factor for axial load because size in this case will not affect my stress. So Kb in this case is 1. For bending and torsion, you can use this formula. This is for SI units. If you have smaller diameter, you use this. If your diameter is between 2.79 and 51 millimeter, you use this formula. And if your diameter is larger, between 51 and 254, then you use this formula for the size factor. The load factor for bending, you remember the test was done using bending only. So if we have bending, then we don't need to correct for the load factor. Load factor will be 1. If we have axial, then we need to correct for the load factor. If we have torsion, we must also use this value for Kc. Ke is the reliability factor. The test specimen has a reliability of 50%, which means if we have 50% reliability, then the reliability factor will be 1. There is no change due to reliability. If we have more reliable, let's say we have 99% reliable machine, then reliability factor KE will be this value, 0.814. Temperature factor, it will depend on the temperature. The ideal test specimen, the test was done at a temperature of 20 degrees Celsius. So in this case, temperature factor is 1. If your temperature is different than 20, let's say machine is working in a temperature of 150 degrees, then you need to correct for temperature factor. Your temperature factor KD would be 1.025 at 150 degrees Celsius. Okay. If you have residual stresses, corrosion, if there is hardening, fatigue, any other factor, any other conditions that you know about, you can include them, and that comes from experience, comes from historical data, and it's only limited by availability of